Reinforced concrete columns are the silent guardians of every structure you see around you: high-rise buildings, bridges, parking structures, and industrial plants. Yet, a single mistake in column design can lead to excessive settlement, cracking, or even catastrophic failure. In this video, we bring you the ultimate guide to designing reinforced concrete columns, explained step by step from a civil engineer's perspective. Whether you are a student preparing for exams, a practicing engineer designing real projects, or a developer planning safe and economical structures, this video will help you understand the fundamental principles, calculations, and design logic behind reinforced concrete columns. Let's begin building knowledge that stands as strong as concrete itself. Welcome to Civil Engineering Edge, the channel where engineering theory meets real-world construction practice. If you are a civil engineering student preparing for exams, a practicing engineer designing structures, or a developer seeking technical clarity, this channel is built specifically for you. Here, we break down complex civil engineering concepts into clear, structured, and practical explanations using a classroom-style teaching approach. At Civil Engineering Edge, our focus is on reinforced concrete design, structural engineering fundamentals, construction technology, and future-ready infrastructure solutions. Every topic is explained step by step, following relevant IS codes and industry-accepted practices, so you not only understand the how, but also the why behind every design decision. Our mission is to help you build strong technical foundations, improve professional confidence, and apply engineering knowledge effectively on site and in design offices. If you believe that engineering excellence comes from clarity, discipline, and continuous learning, then you are in the right place. Introduction. Why reinforced concrete columns matter. In any reinforced concrete structure, columns play a vital and irreplaceable role. They are the primary vertical structural elements responsible for transferring loads from slabs and beams safely down to the foundation and ultimately to the soil. Unlike beams, which mainly resist bending, columns are subjected to a combination of axial compression, bending moments, and in some cases shear forces. Because of this complex stress behavior, columns demand special attention during structural design. Reinforced concrete columns form the backbone of modern construction. From small residential buildings to high-rise towers, bridges, industrial plants, and public infrastructure, columns ensure the overall stability of the structure. If beams and slabs are considered the working components of a building, columns are the support system that keeps everything standing. A failure in a single column can result in disproportionate collapse, making column design one of the most safety-critical responsibilities of a civil engineer. In rapidly growing urban environments, the demand for taller buildings and heavier load-carrying structures has increased significantly. This places enormous responsibility on reinforced concrete columns to perform efficiently under higher axial loads and increased lateral forces due to wind and earthquakes. In seismic regions, columns must not only be strong, but also ductile, meaning they should deform safely without sudden failure. Proper detailing of reinforcement plays a crucial role in achieving this behavior. Moreover, reinforced concrete columns contribute to durability and long-term performance. When designed and constructed correctly, they offer excellent resistance to fire, corrosion, and environmental degradation. Their rigidity helps control excessive deflections and vibrations, ensuring user comfort and serviceability throughout the structure's lifespan. Understanding why reinforced concrete columns matter is the first step toward becoming a responsible structural engineer. This video aims to provide a comprehensive understanding of column behavior, design philosophy, and engineering judgment required to create safe, economical, and durable structures. As we proceed, remember that column design is not just about formulas, it is about safeguarding lives and infrastructure. What are reinforced concrete columns and why are they essential in construction? A reinforced concrete column is a vertical structural member designed primarily to carry compressive loads while also resisting bending moments and shear forces when present. It is composed of concrete, which performs exceptionally well in compression, and steel reinforcement, which provides tensile strength, ductility, and crack control. This composite action allows reinforced concrete columns to withstand complex loading conditions encountered in real-world structures. Columns are essential components of the load transfer mechanism in buildings. Loads from slabs are transferred to beams, from beams to columns, and finally from columns to the foundation. Without columns, there is no safe path for these loads to reach the ground. This makes columns fundamental to the stability and safety of any structure. Reinforced concrete columns are classified based on several criteria, including shape, loading condition, and slenderness. Common shapes include square, rectangular, circular, and special shapes used in architectural designs. Based on loading, columns may be axially loaded, eccentrically loaded, or subjected to combined axial load and bending. Slenderness classification distinguishes between short and long columns, which behave differently under load. The essential nature of reinforced concrete columns becomes even more evident during extreme events such as earthquakes or strong winds. Columns are key elements in resisting lateral forces and preventing collapse. Properly detailed columns with adequate confinement reinforcement can undergo large deformations without losing load carrying capacity, which is a critical requirement in seismic design. Another reason reinforced concrete columns are indispensable is their adaptability in construction. They can be cast in situ or precast, integrated into walls, or designed as isolated architectural elements. Their fire resistance, robustness, and compatibility with other reinforced concrete elements make them ideal for a wide range of applications. In summary, reinforced concrete columns are essential because they provide load transfer, stability, ductility, and durability. Every safe and reliable structure depends on correctly designed and well-constructed columns. Advantages of reinforced concrete columns over other materials. Reinforced concrete columns offer several distinct advantages over columns constructed from alternative materials such as steel, timber, or masonry. One of the most significant advantages is their high compressive strength combined with adequate tensile resistance due to steel reinforcement. This makes reinforced concrete columns capable of supporting heavy loads efficiently, even in multi-story and high-rise structures. Durability is a major advantage of reinforced concrete columns. When designed with proper cover, quality materials, and correct detailing, they can resist environmental effects such as moisture, temperature variation, and chemical exposure. Compared to timber columns, reinforced concrete is not susceptible to decay, termites, or fungal attack. Unlike steel columns, reinforced concrete does not rapidly lose strength when exposed to fire. Fire resistance is a critical safety advantage. Concrete acts as a natural fireproofing material that protects the embedded steel reinforcement. In the event of a fire, reinforced concrete columns retain their load-carrying capacity for a longer duration, providing crucial time for evacuation and emergency response. From an economic standpoint, reinforced concrete columns are often more cost-effective, especially in regions where cement, aggregates, and labor are readily available. They require less frequent maintenance compared to steel columns, reducing life cycle costs. Their long service life makes them a preferred choice for permanent structures. Reinforced concrete columns also offer architectural flexibility. They can be molded into various shapes and sizes to suit architectural layouts without compromising structural safety. Additionally, their stiffness helps control deflections and vibrations, improving overall building performance. Due to these advantages, strength, durability, fire resistance, economy, and flexibility, reinforced concrete columns remain the most widely used column type in civil engineering construction. Importance of proper design for safety and structural integrity. Proper design of reinforced concrete columns is essential to ensure structural safety, stability, and durability throughout the service life of a building. Columns are highly stressed elements, and even minor design or detailing errors can lead to serious structural deficiencies or catastrophic failure. Therefore, column design demands careful analysis, accurate calculations, and strict adherence to design codes such as IS 456. One of the primary goals of column design is to provide adequate load carrying capacity under all possible load combinations. This includes dead loads, live loads, wind loads, seismic forces, and accidental loads. Failure to consider these load combinations can result in underdesigned columns that may crack, buckle, or collapse under service conditions. Structural integrity also depends heavily on proper reinforcement detailing. Longitudinal reinforcement must be sufficient to carry axial and bending stresses, while lateral ties or spirals are necessary to prevent buckling of main bars and to confine concrete. In seismic regions, closely spaced ties improve ductility and energy dissipation capacity. Slenderness effects are another critical consideration. Long columns are prone to buckling, which significantly reduces their load-carrying capacity. Proper evaluation of effective length, end conditions, and slenderness ratios is necessary to ensure stability. Serviceability is equally important. Proper design helps control cracking, deformation, and vibration, ensuring comfort and durability. A well-designed column minimizes maintenance issues and extends the structure's lifespan. Ultimately, proper column design is a matter of public safety. Engineers have a professional responsibility to ensure that columns are designed not just to meet minimum code requirements, but to provide reliable performance under both normal and extreme conditions. A correctly designed reinforced concrete column is a cornerstone of structural integrity and engineering excellence. Understanding the design process. Designing reinforced concrete columns is a systematic and logical engineering process that ensures safety, strength, serviceability, and durability of a structure. Unlike architectural elements, column design cannot rely on assumptions or visual judgment. It must be based on scientific principles, structural analysis, and codal provisions. Understanding the design process is essential before performing any calculations. The column design process begins with understanding the structural system of the building. Columns do not work in isolation. They interact with slabs, beams, walls, and foundations. The position of a column within the structural layout, whether it is a corner column, edge column, or interior column, significantly influences the magnitude and type of forces acting on it. Interior columns typically carry higher axial loads, while edge and corner columns experience greater bending moments due to eccentricity. Next, the nature of loading must be identified. Columns are subjected to dead loads from self-weight of structural and non-structural elements, live loads due to occupancy, and lateral loads from wind and earthquakes. These loads are transferred through slabs and beams into columns, creating complex stress conditions. Proper identification and combination of these loads as per design codes is a critical step in the design process. Material selection is another important component. The grade of concrete and steel directly affects the load-carrying capacity, ductility, and durability of the column. Higher grades of concrete allow for smaller cross-sections, while appropriate steel grades ensure adequate tensile strength and deformation capacity. The design process also considers construction practices. Practical aspects such as reinforcement placement, bar congestion, concreting quality, and workmanship influence final design decisions. A design that is theoretically sound but impractical to construct can lead to poor performance on site. In summary, understanding the column design process means integrating structural behavior, material properties, loading conditions, and construction realities into a unified engineering approach. This foundation ensures accurate calculations and safe structural performance. Factors influencing reinforced concrete column design. Several interrelated factors influence the design of reinforced concrete columns, and understanding these factors is essential for producing safe and efficient structural designs. One of the most significant factors is loading. Columns are subjected to axial loads, bending moments, and sometimes shear forces. These loads originate from dead loads such as self-weight of slabs, beams, walls, and finish, as well as live loads due to occupants, furniture, equipment, and vehicles. In addition, lateral loads from wind and earthquakes induce bending moments and additional axial forces in columns. Material properties play a crucial role in column design. The grade of concrete determines its compressive strength, stiffness, and durability, while the grade of steel reinforcement influences tensile capacity and ductility. Selecting appropriate material grades is a balance between structural efficiency, economy, and construction feasibility. For example, higher concrete grades allow for reduced column sizes, but may require stricter quality control during construction. Geometric factors such as column size, shape, and slenderness ratio also influence design. Slender columns behave differently from short columns and are more susceptible to buckling. The effective length of a column depends on its end conditions and framing system, which must be carefully evaluated. Construction methods significantly affect column design. Whether the column is cast in situ or precast, the method influences detailing, reinforcement placement, and quality control. For workmanship, improper compaction or inadequate curing can reduce the actual strength of the column, even if the design is correct. Environmental exposure is another influencing factor. Columns exposed to aggressive environments require increased concrete cover and durability considerations to prevent corrosion of reinforcement. Thus, column design is influenced by a combination of loads, material properties, geometry, construction practices, and environmental conditions. Ignoring any of these factors can compromise safety and long-term performance. Key design parameters: axial load, bending moment, and shear force. Reinforced concrete column design is governed by three key design parameters: axial load, bending moment, and shear force. These parameters define the internal forces acting on the column and determine the required size and reinforcement. Axial load is the primary force acting on a column and results from the weight of structural and non-structural components supported by the column. Axial compression reduces the effective tensile stresses in concrete, but excessive axial load can lead to crushing failure. Accurate calculation of axial load using proper load combinations is essential for safe design. Bending moment occurs when the line of action of the load does not pass through the centroid of the column section, or when lateral loads act on the structure. Edge and corner columns are particularly susceptible to bending moments due to eccentric loading. Combined axial load and bending is the most common condition in real structures, making it critical to design columns using interaction principles rather than pure axial capacity alone. Shear force in columns is generally smaller compared to beams, but becomes significant in seismic regions and short columns. Shear failure is brittle and sudden, making it highly undesirable. Proper lateral reinforcement ensures adequate shear resistance and confinement. These three parameters are not independent, they interact with each other. Design codes provide interaction diagrams and equations to evaluate column capacity under combined axial load and bending. Proper consideration of these parameters ensures that columns remain safe under all loading conditions. Understanding these key design parameters enables engineers to visualize force flow within the column and design reinforcement that provides both strength and ductility. Importance of codes and standards for safe and reliable design. Codes and standards form the backbone of safe and reliable reinforced concrete column design. They represent decades of research, experimental data, and real-world failure analysis translated into practical design rules. Adhering to design codes such as IS 456 is not optional. It is a professional and legal responsibility of every civil engineer. Design codes provide standardized methods for calculating loads, selecting material strengths, and applying safety factors. They ensure consistency in design practices across projects and help engineers achieve acceptable levels of safety and serviceability. Without codal guidance, designs would vary significantly, increasing the risk of structural failure. Codes also address detailing requirements, which are critical for column performance. Specifications for minimum and maximum reinforcement, spacing of lateral ties, concrete cover, and anchorage lengths ensure ductility and prevent brittle failure modes. In seismic zones, additional provisions enhance energy dissipation and confinement. Another key role of codes is risk management. By using partial safety factors and load combinations, codes account for uncertainties in material strength, construction quality, and loading conditions. This ensures that structures can withstand unexpected variations without collapse. Compliance with codes also protects engineers legally and ethically. In the event of structural distress or failure, adherence to recognized standards demonstrates professional due diligence. In conclusion, design codes and standards are essential tools that transform engineering knowledge into safe, economical, and reliable structures. Proper application of these codes ensures that reinforced concrete columns perform as intended throughout their service life.
Concrete and reinforcement requirements. Concrete and steel reinforcement together form the fundamental materials of reinforced concrete columns. Their combined action enables columns to resist complex combinations of compressive, tensile bending, and shear forces. Understanding the material behavior and requirements of both concrete and reinforcement is essential for designing safe, durable, and economical columns. Concrete primarily resists compressive stresses and provides stiffness and mass to the column. It also protects embedded steel reinforcement from corrosion and fire. However, concrete alone is weak in tension and prone to cracking. This limitation is overcome by introducing steel reinforcement, which has high tensile strength and ductility. The interaction between concrete and steel ensures load sharing and strain compatibility under service and ultimate load conditions. In column design, material selection is governed by design loads, exposure conditions, and codal provisions. The grade of concrete determines the compressive strength, while the grade of steel influences tensile capacity and ductility. Proper proportioning of these materials ensures adequate load-carrying capacity without unnecessary increase in column size or reinforcement congestion. Concrete and reinforcement requirements also directly affect construction quality. Adequate concrete cover, proper bar spacing, and good compaction are necessary to achieve the designed strength. Poor material selection or improper detailing can compromise structural performance, even if calculations are correct. This section focuses on understanding the properties of concrete, the types and behavior of reinforcement bars, and how to select appropriate materials based on design parameters. A clear grasp of these aspects enables engineers to make informed design decisions that balance strength, durability, constructability, and economy. Properties of concrete and its role in resisting compressive forces. Concrete is the primary load-resisting material in reinforced concrete columns, particularly under compressive forces. It is a composite material made from cement, fine aggregates, coarse aggregates, water, and sometimes admixtures. Once hardened, concrete exhibits high compressive strength, making it ideal for vertical load-bearing elements such as columns. One of the most important properties of concrete in column design is its compressive strength, usually represented by its characteristic strength, such as M20, M25, M30, and higher grades. This strength determines the maximum compressive stress the concrete can safely carry. Higher concrete grades allow columns to support greater loads with smaller cross-sections, which is particularly useful in high-rise buildings where space efficiency is critical. Concrete also provides stiffness to columns, reducing deformation under load. This stiffness helps control excessive shortening and prevents instability, especially in short columns. Additionally, concrete contributes to the overall mass of the structure, which can influence seismic behavior by affecting natural periods and damping. Another vital role of concrete is protecting the embedded steel reinforcement. Concrete cover shields steel from corrosion caused by moisture and aggressive chemicals. It also provides excellent fire resistance by insulating the steel and delaying strength loss during fire exposure. However, concrete has limitations. It is weak in tension and brittle in nature, meaning it cracks easily under tensile stress and fails suddenly if overloaded in compression. This brittleness is mitigated by steel reinforcement, which provides ductility and warning before failure. Durability is another critical property of concrete. Proper mix design, adequate curing, and suitable cover ensure resistance to environmental exposure, chemical attack, and long-term deterioration. In summary, concrete plays a dominant role in resisting compressive forces, providing stiffness, durability, fire resistance, and protection to reinforcement. Its proper selection and quality control are fundamental to safe column performance.
Types of reinforcement bars and their role in resisting tensile forces. Steel reinforcement is introduced into concrete columns primarily to resist tensile forces and enhance ductility. Since concrete is weak in tension, reinforcement bars carry tensile stresses caused by bending moments, eccentric loads, and lateral forces. They also help control cracking and improve overall structural behavior. The most commonly used reinforcement bars in reinforced concrete columns are mild steel bars and high-strength deformed bars. Mild steel bars, though ductile, are rarely used in modern construction due to their lower strength. High-strength deformed bars, such as Fe 415, Fe 500, and Fe 550 are widely used because of their superior tensile strength and bond characteristics. Deformed bars have ribs on their surface, which improve the bond between steel and concrete. This bond ensures effective stress transfer and prevents slippage under load. Higher grade steel allows for reduced reinforcement area, making designs more economical and reducing congestion in heavily reinforced columns. Reinforcement in columns is divided into longitudinal reinforcement and transverse reinforcement. Longitudinal bars carry axial loads and bending stresses, while transverse reinforcement such as ties or spirals provides confinement, prevents buckling of longitudinal bars, and enhances ductility. In seismic regions, closely spaced ties are essential to prevent sudden brittle failure. Steel reinforcement also plays a critical role in energy dissipation during earthquakes. Ductile steel allows columns to undergo large deformations while maintaining load-carrying capacity. This behavior is crucial for preventing collapse during seismic events. Corrosion resistance is another important consideration. Although steel is prone to corrosion, proper concrete cover and quality concrete significantly reduce this risk. Thus, reinforcement bars are indispensable in resisting tensile forces, ensuring ductility, controlling cracks, and enhancing safety. Selecting the right type and detailing it properly is essential for effective column performance. Selection of concrete mix and reinforcement based on design parameters. Selecting the appropriate concrete mix and reinforcement for reinforced concrete columns is a critical design decision that directly affects strength, durability, and economy. This selection must be based on design loads, exposure conditions, construction practices, and codal requirements. The concrete mix is chosen primarily based on required compressive strength and durability. For residential and low-rise buildings, M20 or M25 concrete is commonly used. For high-rise structures and heavily loaded columns, higher grades such as M30 or above may be required. Exposure conditions, such as marine environments or industrial areas, may necessitate higher grades and additional durability measures. Workability is another key factor. Columns with congested reinforcement require workable concrete to ensure proper compaction. Admixtures may be used to improve workability without increasing water content, which would otherwise reduce strength. Reinforcement selection depends on axial load, bending moment, and slenderness of the column. Higher loads and moments require greater reinforcement area. High-strength steel grades such as Fe500 are commonly used to reduce reinforcement quantity while maintaining strength. Codal limits on minimum and maximum reinforcement percentages must be followed to ensure ductility and prevent congestion. Transverse reinforcement spacing is selected based on column size, reinforcement diameter, and seismic requirements. Constructability should also be considered. Excessive reinforcement can make placing and compacting concrete difficult, leading to honeycombing and reduced strength. In conclusion, selecting the right concrete mix and reinforcement is a balance between structural demand, durability, economy, and construction practicality. Proper selection ensures that columns perform safely and efficiently throughout their service life. Practical considerations and best practices. While structural design calculations are essential, the real performance of reinforced concrete columns largely depends on practical execution on site. Even a perfectly designed column can fail to perform as intended if construction practices, detailing, and quality control are inadequate. Therefore, civil engineers must understand not only theoretical design principles, but also practical considerations and best practices that ensure safe and durable construction. Practical considerations begin at the detailing stage. Reinforcement detailing must be clear, code compliant, and easy to execute on site. Poor detailing can result in congestion, improper bar placement, and inadequate compaction of concrete. These issues can significantly reduce the load-carrying capacity of columns and lead to durability problems over time. Construction practices such as accurate placement of reinforcement, proper alignment of formwork, and adequate compaction of concrete directly influence column strength and serviceability. Site constraints, labor skills, and environmental conditions must be considered during execution. Engineers should ensure that drawings are practical and that site teams understand the importance of following them precisely. Durability is another major concern. Exposure to moisture, chemicals, and temperature variations can deteriorate reinforced concrete columns if proper measures are not taken. Adequate concrete cover, correct mix design, and effective curing practices are essential to protect reinforcement from corrosion and ensure long-term performance. Quality control measures, including material testing, inspection of reinforcement, and supervision during concreting, play a crucial role in achieving the desired performance. Construction tolerances must be controlled to ensure that the as-built structure matches design assumptions. This section focuses on best practices related to reinforcement detailing, concrete cover, and on-site execution. Applying these practices ensures that reinforced concrete columns perform reliably throughout their service life. Detailing and placement of reinforcement bars for proper bond and load transfer. Proper detailing and placement of reinforcement bars are critical for ensuring effective bond between steel and concrete and reliable transfer of loads within reinforced concrete columns. Even minor errors in reinforcement detailing can lead to stress concentration, premature cracking, or loss of load carrying capacity. One of the most important aspects of reinforcement detailing is maintaining correct bar spacing. Adequate spacing ensures that concrete can flow easily around the bars during placement and compaction. Congested reinforcement restricts concrete flow, leading to honeycombing and weak zones. Codes specify minimum clear spacing between bars to avoid such issues, and these requirements must be strictly followed. Anchorage and development length are equally important. Reinforcement bars must be embedded sufficiently into the concrete to develop their full tensile strength. In columns, longitudinal bars should be continuous wherever possible, with splices located away from regions of maximum stress. When lap splices are necessary, they should be staggered and detailed as per codal provisions to avoid sudden strength reduction. Transverse reinforcement, such as lateral ties or spirals, plays a crucial role in confinement and load transfer. Ties prevent buckling of longitudinal bars under compression and improve ductility by confining the concrete core. Proper spacing and secure fastening of ties ensure effective confinement, especially in seismic regions. Bar placement accuracy is also critical. Misaligned bars reduce effective cover and can introduce unintended eccentricity, affecting column behavior. Use of spacers and chairs helps maintain correct bar positioning during concreting. In practice, clear reinforcement drawings, proper supervision, and skilled workmanship are essential to achieve correct detailing and placement. Proper reinforcement detailing ensures effective bond, uniform stress distribution, and safe load transfer within columns. Practical considerations and best practices. While structural design calculations are essential, the real performance of reinforced concrete columns largely depends on practical execution on site. Even a perfectly designed column can fail to perform as intended if construction practices, detailing, and quality control are inadequate. Therefore, civil engineers must understand not only theoretical design principles, but also practical considerations and best practices that ensure safe and durable construction. Practical considerations begin at the detailing stage. Reinforcement detailing must be clear, code compliant, and easy to execute on site. Poor detailing can result in congestion, improper bar placement, and inadequate compaction of concrete. These issues can significantly reduce the load carrying capacity of columns and lead to durability problems over time. Construction practices such as accurate placement of reinforcement, proper alignment of formwork, and adequate compaction of concrete directly influence column strength and serviceability. Site constraints, labor skills, and environmental conditions must be considered during execution. Engineers should ensure that drawings are practical and that site teams understand the importance of following them precisely. Durability is another major concern. Exposure to moisture, chemicals, and temperature variations can deteriorate reinforced concrete columns if proper measures are not taken. Adequate concrete cover, correct mix design, and effective curing practices are essential to protect reinforcement from corrosion and ensure long-term performance. Quality control measures, including material testing, inspection of reinforcement, and supervision during concreting, play a crucial role in achieving the desired performance. Construction tolerances must be controlled to ensure that the as-built structure matches design assumptions. This section focuses on best practices related to reinforcement detailing, concrete cover, and on-site execution. Applying these practices ensures that reinforced concrete columns perform reliably throughout their service life. Detailing and placement of reinforcement bars for proper bond and load transfer. Proper detailing and placement of reinforcement bars are critical for ensuring effective bond between steel and concrete and reliable transfer of loads within reinforced concrete columns. Even minor errors in reinforcement detailing can lead to stress concentration, premature cracking, or loss of load carrying capacity. One of the most important aspects of reinforcement detailing is maintaining correct bar spacing. Adequate spacing ensures that concrete can flow easily around the bars during placement and compaction. Congested reinforcement restricts concrete flow, leading to honeycombing and weak zones. Codes specify minimum clear spacing between bars to avoid such issues, and these requirements must be strictly followed. Anchorage and development length are equally important. Reinforcement bars must be embedded sufficiently into the concrete to develop their full tensile strength. In columns, longitudinal bars should be continuous wherever possible, with splices located away from regions of maximum stress. When lap splices are necessary, they should be staggered and detailed as per codal provisions to avoid sudden strength reduction. Transverse reinforcement, such as lateral ties or spirals, plays a crucial role in confinement and load transfer. Ties prevent buckling of longitudinal bars under compression and improve ductility by confining the concrete core. Proper spacing and secure fastening of ties ensure effective confinement, especially in seismic regions. Bar placement accuracy is also critical. Misaligned bars reduce effective cover and can introduce unintended eccentricity, affecting column behavior. Use of spacers and chairs helps maintain correct bar positioning during concreting. In practice, clear reinforcement drawings, proper supervision, and skilled workmanship are essential to achieve correct detailing and placement. Proper reinforcement detailing ensures effective bond, uniform stress distribution, and safe load transfer within columns. Importance of concrete cover for corrosion protection and durability. Concrete cover is the thickness of concrete provided between the surface of the reinforcement and the outer surface of the concrete member. It plays a vital role in protecting steel reinforcement from corrosion, fire exposure, and environmental deterioration. Adequate concrete cover is essential for ensuring the durability and long-term performance of reinforced concrete columns. One of the primary functions of concrete cover is corrosion protection. Steel reinforcement is susceptible to corrosion when exposed to moisture, oxygen, and aggressive chemicals. Concrete acts as a protective barrier, preventing these agents from reaching the steel. Insufficient cover can lead to early corrosion, causing expansion of steel, cracking of concrete, and reduction in structural capacity. Concrete cover also contributes to fire resistance. During fire exposure, the cover insulates the steel reinforcement, delaying temperature rise and preventing rapid loss of strength. Columns with inadequate cover may experience premature failure during fire events. Durability requirements vary based on exposure conditions. Columns in marine environments, industrial areas, or areas with high humidity require increased cover to withstand aggressive conditions. Design codes specify minimum cover requirements based on exposure classification, which must be strictly followed. Excessive cover, however, is also undesirable. Too much cover can reduce effective depth and increase cracking due to shrinkage and temperature effects. Therefore, providing the correct cover as per design and code is essential. Proper placement of cover blocks and spacers ensures uniform cover throughout the column. Poor workmanship can lead to variable cover, reducing effectiveness. In summary, concrete cover is a critical durability parameter that protects reinforcement, enhances fire resistance, and ensures long-term performance. Adequate cover, combined with quality concrete and proper curing, significantly increases the service life of reinforced concrete columns. Construction tolerances, formwork design, and quality control measures. Practical construction considerations such as tolerances, formwork design, and quality control have a direct impact on the performance of reinforced concrete columns. Design assumptions are valid only if construction adheres closely to specified dimensions and detailing. Construction tolerances refer to acceptable deviations in dimensions, alignment, and positioning of columns. Excessive deviation can introduce unintended eccentricity, increasing bending moments and reducing load carrying capacity. Engineers must ensure that tolerances remain within permissible limits through proper setting out and supervision. Formwork design is another crucial aspect. Formwork must be strong enough to resist lateral pressure from fresh concrete without excessive deflection. Poorly designed formwork can lead to bulging, misalignment, or leakage of cement paste, affecting column dimensions and surface quality. Proper alignment and tight joints ensure dimensional accuracy and good surface finish. Quality control measures ensure that materials and workmanship meet design requirements. Concrete quality must be verified through slump tests, Q-Bay tests, and proper curing practices. Reinforcement should be inspected for correct grade, diameter, spacing, and placement before concreting. Supervision during concreting is essential to ensure proper compaction using vibrators and to avoid segregation. Inadequate compaction leads to voids and honeycombing, which significantly reduce strength and durability. Documentation and inspection records provide accountability and help identify issues early. Regular quality checks ensure that reinforced concrete columns achieve their intended performance. In conclusion, strict control of construction tolerances, well-designed formwork, and effective quality control are essential best practices that bridge the gap between design and real-world performance. Conclusions. Reinforced concrete column design is one of the most critical responsibilities of a civil engineer, as columns directly influence the safety, stability, and longevity of any structure. Throughout this video, we have explored the complete journey of reinforced concrete column design, from understanding their structural importance and material behavior to practical detailing, construction considerations, and best practices. This holistic understanding is essential because column performance depends not only on calculations, but also on sound engineering judgment and quality execution. A well-designed, reinforced concrete column ensures safe transfer of loads from the superstructure to the foundation, while maintaining adequate strength under axial loads, bending moments, and shear forces. Proper selection of concrete grade, reinforcement type, and detailing methods enhances ductility and durability, especially in regions exposed to seismic activity and harsh environmental conditions. Adherence to design codes and standards provides a systematic approach to managing uncertainties and ensuring reliable structural performance. Equally important are practical considerations such as reinforcement placement, concrete cover, formwork accuracy, and quality control. These factors bridge the gap between design assumptions and actual on-site behavior. Many structural failures originate not from poor design theory, but from inadequate detailing, poor workmanship, or lack of supervision during construction. Understanding this reality empowers engineers to design structures that perform as intended throughout their service life. Reinforced concrete column design is not merely a procedural task, it is an ethical responsibility. Engineers must prioritize public safety while balancing economy and constructability. Continuous learning, awareness of updated codes, and learning from past failures help engineers refine their skills and judgment. In conclusion, mastering reinforced concrete column design requires a strong foundation in theory, practical knowledge of materials and construction practices, and strict adherence to codes. When these elements work together, they result in structures that are safe, durable, and capable of serving society for decades. As civil engineers, our goal is not just to design structures, but to design trust, safety, and reliability into every column we build. Thank you for watching this detailed guide on reinforced concrete column design, exclusively brought to you by Civil Engineering Edge. We hope this video has strengthened your understanding of column behavior, design principles, material requirements, and practical execution on site. Remember, every safe structure begins with well-designed columns, and every great engineer understands the responsibility behind each design decision. If you found this video helpful, don't forget to like, share, and subscribe to Civil Engineering Edge for more in-depth civil engineering tutorials, real-world design explanations, and classroom-style learning content. Your support helps us continue creating high-quality educational videos for the engineering community. Stay connected with us as we explore advanced structural concepts, his code-based designs, construction best practices, and future infrastructure technologies. Until next time, keep learning, keep building, and keep pushing your engineering knowledge to the next level only on Civil Engineering Edge.